Hello everyone. In this video, I will go over my solution for the problem named Doremy city construction taken from the global round. This problem is an excellent problem which teaches you how to greedily maximize the number of edges in a bipartite graph. As I'll be explaining shortly, this graph is actually a bipartite graph, although you need to deduce that by making some observations from the problem statement. And we need to find the maximum number of edges which we can create. So we need to use a kind of greedy algorithm in order to maximize this quantity. So in this problem, we are basically given altitudes of each vertex for n different vertices, and we need to use these vertices to create a graph. We can add edges between elements such that this condition is met. So the only condition which should be met is that there should not be three distinct vertices such that they are connected together. So u to v and v to u are connected. So it's like a line, and the elements in the line are in increasing order or in non-decreasing order. So there cannot be three edges u, v, and w such that AU is less than or equal to AV is less than or equal to AW. So if AU less than or equal to AV is less than or equal to AW exists, then this construction is not valid. So this is an example of an invalid graph, and we need to find out the maximum number of possible edges in a graph such that only this condition is not met. We can use any other possible uh, possible edges in the graph. So let's take an example. Let's say that we have the elements 2, 2, 3, 1. Obviously, the first step when you notice this inequalities in values, you'll obviously first sort the elements in the set A because it just makes it so much easier to think about these inequalities. So if you sort the elements in the first example, you'll get 1, 1, 2, 3. I mean 1, 2, 2, 3. And because the order doesn't matter, like the indices themselves don't matter, you don't need to print the graph. You just need to find the number of edges in the graph. That's why once you sort the elements, you don't need to worry about the indices. You can just rename them as 1, 2, 3, 4. And you can see that there's an edge. So one possible graph is in which there's an edge between the first index and the second index, because 1 is less than or equal to 2. Now once this condition that 1 is less than or equal to 2 is met, you cannot add 2 and 3 or 2 and 4. So this won't be valid because a1 is less than or equal to a2 and a2 is less than or equal to a3. So this is invalid. Similarly, 2, 4 is also invalid because you'll get a line in which the inequalities condition is met. So you don't want that condition to be met. That's why once you join 1, 2, you can't join anything else to 2. You can join elements to 1, though. You can join 1, 3, and you can join 1, 4. So this is a possibility. So it turns out that this is the maximum possible number of edges you can put. So you can only put 3 edges, and you can see that there are multiple possible constructions which are valid, and this is invalid. So that's the first example. The last example is an example for border case. So they made it a little bit easier by giving this border case. Otherwise, you could be debugging forever if you didn't know that there is a case in which all the elements are equal. So if all the elements are equal, so let's handle this border case itself now so that we can go on to the general case, which is slightly easier. I mean, which is more easy to think about. The border case is in which all elements are equal. So if all elements are equal, this means that you can, so let's say all the elements are equal to, in this case, all the elements are equal to, I think, 1 million. There are 6 zeros, so yeah, 1 million. And it doesn't matter what they are equal to, just the fact that all of them are equal means that, so let's say you have 4 elements, 1, 2, 3, 4. It means that you cannot have more than 2 nodes in a set. So you can't have 1, 2, 3. You can only have 1, 2, and you can't add any more edges to any of them. So similarly, you'll add 3, 4. and you can't add any more edges to them. And if you add more elements, for example 5, 6, you can put 5, 6 in a separate component, but you can't add any elements, any more elements to this. If you add 7, you couldn't add 7 anywhere. So 7 would just be alone like this. So you can see that in this border case, when all elements are equal, you have to form pairs of elements, because once you add the third element, the condition that AU less than or equal to AV less than or equal to AW will be met, because AU is equal to AV is equal to AW. So you cannot have any three elements which touch each other. So if all elements are equal, you just print n by 2, because there are n by 2 pairs. And uh, this works even for odd n, because for odd n you just take the floor of this. So for example, if it was 7, there are just 3 pairs. You can't add a third element to any of these pairs. So this is the border case when all elements are equal. When all elements are not equal, when there are some unequal elements, then the problem actually becomes a problem in which you need to construct a bipartite graph. I'll be explaining briefly what a bipartite graph is and why this condition basically means that you need to create a bipartite graph. So first, let's return to the original constraint. The original constraint was that if you have two nodes connected U and V, we need to ensure that V is not connected to a node W such that AU is less than or equal to AV is less than or equal to AW. So this means that if you assume AU is already less than or equal to AV without loss of generality, because for example, if you connected 1 with 2, and you basically, since you have sorted the array, you know that A1 is less than or equal to A2. So already this first condition is met. This means that you cannot add another element A3 to this graph, because once we have sorted the elements, A2 is less than or equal to A3. So this basically means that we cannot add elements. We cannot add an edge between V and W once you have U and V connected. And this basically means that W is in the same set as U. So W and U are in the same set, and there cannot be, W and V are in the same set because there are no edges between V and W. And over here is a good place to explain what a bipartite graph is. So a bipartite graph is basically a graph in which all the nodes are divided into two sets. Let's call the sets A and B. So all the nodes are divided into two sets A and B, such that all the edges go from A to B. So all the edges go between A and B, and there are no edges within A or no edges within B. So if you apply this definition to this graph, you can see that U and W, V and W cannot be in the same set because there cannot be this edge between them. So this means that, so V and W have to be in the same set because there cannot be an edge between them. And U and V are in opposite sets. So let's say that U is in set A. This means that V is in the opposite set B, and W is also in the set B. So we can get this type of, you can understand this constraint in terms of a bipartite graph, because if you add more edges, you will realize that similarly you cannot add, let's say you have another edge X. So if you add an edge between U and X, this means that X also belongs to the second component, and we necessarily need to ensure that X, so since X is in the second component, X should be greater than AU. So AX should be greater than AU, because if AX is less than AU, or if AX is equal to AU, then you'll get this line, this sequence of AX less than or equal to AU less than or equal to AV. So basically what I'm saying is that you cannot, so if you reconsider the edge between u and v, and if you assume AU is less than or equal to AV without loss of generality, you can see that you cannot add an edge x such that AX is less than or equal to AU. So if you have an edge from x to u, you need to ensure that AX is greater than AU. This is the first condition. And if you have an edge between v and some w, you need to ensure that AV is less than, AW is less than AV, because if AW is greater than or equal to AV, then you form this line in which the three elements are connected in a line and they are in increasing order. So this basically means that if you consider this graph, then U is part of set A, V is part of set B, X is part of set B, and W is part of set A, because the edges are only from A to B, and within B and within A there are no edges. And this helps us because there is something special about sets A and B. If you look closely at all these inequality conditions which need to be satisfied, you'll see that set A has all those elements which are small. Set A has nodes U and W, and we know that AW is less than AV, and we know that AU is less than or equal to AV. And set B has all those elements which are big. We know that AX is greater than AU, and AV is greater than or equal to AU. This means that if you consider the big graph, if you consider the big picture of the whole array, set A will always contain those small elements, and set B will always contain those large elements. So it's clear that if you consider some edge U to V, and if you consider a strict inequality, let's put a strict inequality over here, because we know that all those elements are not the same. So we have handled the border case in which all the elements are the same. Now we know that all the elements are not the same. That's why we can remove this strict, we can remove the equal to and make our job simpler. And now you should see something very clearly stand out. It should become obvious to you that we are splitting the elements into two sets based on which elements are smaller and based on which elements are bigger. This means that if you consider some splitting point, so if you take some position I, then if you take some position I, then all elements at positions less than or equal to I, so at position less than or equal to I, are in set A. They form set A because we know that set A contains all the small elements, and all elements after position I, so all elements after I are in set B. And because we know that the edge, we know that we can connect all elements from set A to set B, so that's why we can form the largest number of edges. I'll be explaining that now. Notice that once you have sets A and B, you can actually connect all elements in set A with all elements in set B. So if we draw this graph over here, UV and XW, so if you have X and W over here, U is part of U, and so U and the other node, U is part of set A, V is part of set B, and W is part of set A, and X is part of set B. So if you consider these two sets, then you'll notice that you can connect all elements between, you can collect all pairs of elements. So you can connect U to V, U to X, W to V, W to X, because these are all strict inequalities. So AU is less than AV, AU is less than AX, AW is less than AV, and AW is less than AX. So because we have sorted the elements and we have split them into two halves based on some pivot I, we know that we can connect all elements in the first half with all the elements in the second half, and that's why the number of edges, So the number of edges is going to be equal to I into n minus I. So if there are I elements, we know that all elements at positions less than or equal to I come in the first set. So this means that size of set A is equal to I, so I elements, and all the remaining elements come in set B, so n minus I elements, and that's why n minus I elements into I elements will give us the total size of the set. At this point, you should pause the video and actually try out the remaining examples, the remaining samples, and try to find the two sets A and B. Remember that the two sets A and B should be disjoint, so like they should be distinct. All the elements up to some index I should be in set A, and all elements after that index I should be in set B. And remember that you can connect all elements between these two sets, all pairs of elements, because if you notice the condition, the first set contains only small elements, and the second set contains only large elements, and you're not going across sets, you're not going like within sets, and that's why all these possible edges need to be considered. And this is the entire logic. So you should pause the video, try this logic on the examples, and now I'll show you the code which basically does this. It iterates over all possible values of I, and I'll show you how you can efficiently compute this in the code. So in the code for each test case, I take in the number of elements in the array, I input all the altitudes of the vertices, I sort the elements, and I do the initial border case check. So in the border case, we know that we can split all the elements into pairs and connect only elements in a pair. So that's why there are n by 2 pairs. If n is odd, one element will be left out. Otherwise, there are always n by 2 pairs. So you print n by 2 and you continue. So other than this border case, we know that there are going to be distinct elements. Like there will be at least one element which is different from the other elements. So that's why we can run the algorithm on the remaining elements. So the algorithm has a very short code. So what I basically do is I go for each I from 1 to n. I initially put the value. So this is the value of the current element, and I ensure that all elements with the same value are part of the first set. So there are I elements in the first set and n minus I elements in the second set. And because we want to make sure that the inequalities are strict, we need to ensure that whenever we have equality, whenever we have ai equal to the starting element, we need to increase I. And obviously, like the moment this condition breaks, so either I becomes n plus 1 or ai becomes a new value, we'll break out of the loop, and we'll reach 1 greater than the index of the last element of the first set. That's why we need to decrease I by 1, and we set answer to be the maximum of answer comma I times n minus I. So I is the size of the first set, because all elements from 1 to I are part of the set A, and n minus I is the size of the second set, because all the elements from I plus 1 to n are part of set B, and based on the product of the size of the sets, we can compute that the product of the size of the sets is the number of elements, because each and every node in the first set can be connected with each and every node in the second set. And in the end, we just print this answer with the backslash n. So I hope you like this problem and my solution. If you have any doubts in any part of the solution, do leave them in the comments down below. And if you like this video, don't forget to give it a thumbs up. Thank you.